Hello everyone, I am Dr. B.B. Professor and Head in Instrumentation and Control Engineering Department at D.Y. Patil College of Engineering, Akoti, Pune. Well, in this lecture we will discuss about transfer function modeling and fundamentals of block diagram representation. We will begin with the definition of transfer function. In this, a linear time invariant system are under consideration. LTI system means the parameter of system does not vary with respect to time. For example, weight, mass. If it is an electrical system, then resistance, capacitance, they does not vary with respect to time. So the transfer function of such system is the ratio of Laplace transform of output to the Laplace transform of input at zero initial conditions. Let's we have a system with u of t as a time domain input and y of t as a time domain output. Then mathematically, if u of s is a Laplace transform of input and y of s is Laplace transform of output of a system, then its transfer function g of s is given by a ratio y of s to u of s. To find the Laplace transform of any system, the generalized procedure is given here. First of all, get the operating equation of that system with the help of some basic laws. In case of electrical system, Kirchhoff's current and Kirchhoff's voltage law can be used as a basic equations to get model equations. In case of mechanical system, the modeling equations can be obtained from the Newtonian equations or the first principle of system. Once we have model equations, then let us identify the system input and output. In case of multi-input, multi-output system, we have to choose certain set of inputs and outputs. Here we will make our situation simple. We will deal with the seesaw kind of system in which there is a single input and single output. So having input and output variables, take the Laplace transform of model equations at zero initial conditions and then get appropriate ratio of Laplace transform of output to the Laplace transform of input of system. So we will have, suppose, a simple situation like a single loop having RLC circuit which is excited by Vi of t as input voltage. In this case, to find out V0 of t or to find out loop current I of t can be the output variable. We will make our situation, we will keep our situation simple. For example, Vi of t is input. So let's have a modeling equation using Kirchhoff's voltage law for this loop. So Vi of t can be distributed sum across R, sum across L and sum across capacitor. So Vi of t estimate can be given as R into I of t plus L di by dt plus 1 over C into integral of it. Similarly, the only output voltage estimate can be given as V0 of t is equals to 1 over C integral of I dt. So, after these model equations with us, let us choose input and output variable. In this case, Vi of t is the input voltage as an input variable and V0 of t is the estimate of output as an output variable. So now take the Laplace transform of these two equations assuming zero initial conditions. So for equation 1 we have Vi of s is equals to R, which is a fixed, not time varying. So R I of s plus s into L I of s plus 1 upon s into C whole multiplied by I of s. Also we have the Laplace transform of output as a V0 of S is equals to 1 over S into C into I of S. So finally get the Laplace transform as a ratio V0 of S upon Vi of S, and after simplification we will get the simplified form of G of S as the transfer function of this system is equals to 1 over S square L into S L into C plus S into R into C plus 1. Take another example. In this case, the system is described by a form of differential equation. We have a third order differential equation to describe the dynamic of system, which is d cube y d upon dt cube plus 10 d square y by dt square minus 5 into dy by dt plus y, which is equals to 10 du by dt plus u. For simplicity, independent variable t is not shown. Here clearly the output is y of t or y and input is u of t or u. So the situation is very simple. We have model equation, we have input and output variables. So let's have a Laplace transform of this operating equation. So taking Laplace transform of both sides, we will get y of s, and the remainder is shown in square bracket of each term as s cube plus 10s square minus 5s plus 1 bracket complete, which is equals to the Laplace transform of right hand side as a u of s, and the remainder is 10s plus 1 in bracket. I hope this is clear to you as a simplified Laplace transform. So then rearrange the Laplace transform for the ratio y of s by u of s as a Laplace transform system. So we will get the rearrangement in the form as a 10s plus 1 upon s cube plus 10s square minus 5s plus 1. Now let us generalize the situation. The generalized form of a system as a transfer function is given as g of s is equals to, there is a denominator polynomial and there is a numerator polynomial for the number of poles and zeros respectively. So here the ratio is given as b0 s cube s raised to m plus b1 s raised to m minus 1 plus up to bm upon a0 s raised to n plus a1 s raised to n minus 1 plus up to an. So clearly we have m zeros and n poles. Another form of the transfer function as a generalized form of system is expressed in the form of gain, zeros and poles, which is given as k multiplied by s minus z1, s minus z2, s minus zm upon s minus p1, s minus p2 up to s minus pn. So clearly we have the m zeros and n poles of the system. Looking at the order of system, the highest power at denominator is n. So the order of system is n. We have static gain or DC gain of the system, and we have m poles and m zeros and n poles of the system. Now the requirement is that the number of poles should be greater than, or they may be equals to zeros. If number of zeros are more than number of poles, then system cannot be physically realizable, or it requires prediction of some of the information. So normally for the practical systems, the number of poles should be greater than, or they might be equals to number of zeros. Now another think about why this name pole is given or zero is given for those storage elements. So typically the poles are nothing but the roots of denominator polynomial, and we have n number of poles in the last expression. So if you put any value of pole in system transfer function, then system transfer function becomes infinity, that is unbounded. Or if you put the value of 0 in system transfer function, then system transfer function becomes 0. That's why the name 0 is given. And the meaning of unbounded or infinity is a pole. So pole having infinity height, that's the idea behind the name pole. So to understand the pole and zeros, let us take very specific case. In an example, we will consider one gain, 1 0 and 2 poles. So clearly we have gain, a DC gain as 9. Number of poles are 2, which are located at -6 and -18. I hope this is clear to you, and for that purpose we have to equate each term of denominator or numerator equals to 0 to get the actual positions. So pole locations -6, -18, and the 0 location is at -3. So you put this in pole 0 plot in complex domain, then the all poles and 0 they appears in the left hand side. So to understand the meaning of 0, if you put s is equals to -3, which is the location of 0 in this example. So if you put s is equals to -3, then this transfer function vanishes or it becomes 0, and that's why the term is called as a 0. Similarly, if you put any pole location as a s value, in this case either -6 or -18, then the transfer function becomes infinity or also called as unbounded. So it means that the term is a pole, and the significance of pole is the value having infinity value or the pole with infinity height. So let's have another example. The system is now expressed as another expression in which the numerator term is 6s plus 12 upon s cube plus 3s square plus 7s plus 5. So let us identify pole, zeros and gain from this transfer function. To find out the gain, DC gain of system, put s is equals to 0, and if you put s is equals to 0, then remainder at numerator is 12, and at denominator the s term disappears and the remainder is 5. So effectively we will have k is equals to 12 by 5. Similarly, equate numerator is equals to 0 and you will get the location of 0. Here s is equals to -12 upon 6, therefore the 0 location is at -2, and similarly get the poles from the polynomial of denominator. Here we have 3 poles, one at s is equals to -1, second and third poles, they are conjugate pairs and they appears at -1 plus 2j, and the location of third pole is at -1 2j. So let us summarize. The transfer function of system is a ratio of Laplace transform of output to input, and to obtain it is a four-step procedure: get modeling equation, identify input output variables, and taking Laplace transform of model equations, take appropriate ratio so that we will have transfer function g of s as a Laplace transform of output to input. So in the next lecture we will have the another important representation.